Thank you for being here. My name is Ilija Vukorep. I'm chair for digital design methods at BTU Cottbus. And together with Mohamed Abdelaziz and Deena El-Mahdy, we did a paper on exploring extreme 3D printed clay overhangs with integrated active or hot air drying system on a robotic arm. It's a very clumsy, maybe title wrong, long one, but we didn't know how to name it in a different way. It's about, in fact, how we can build really good overhangs without supporting material in 3D printing, clay. What it's about? We have a growing need in the industry for earth constructions, building with earth, and also with this we connected with 3D printing. And a problem here is a little bit that we have an overhang limit when we build with clay. So it's just because the material is wet and the material stability and the gluing of each layer is not working so well when the material is so wet and it's not stable, it can fall down. So the drying is a critical thing for improving the strength and the shape retention. So there are some papers also dealing with this, but not in main. They are like inside of some papers. They are like chapters that deals with this topic. And so we wanted to actively, like let's say, deal with just the thing and try to solve it somehow. And the goal was to develop a system that works with it. So what were the objectives? We had to improve the stability of overhang geometries and to explore the maximum angle of without failure. So what is the maximum angle we could do with some air drying system? What we used is a robotic arm, and I will show it in a moment how the setup was built up. But here you see we did build up some 3D models that were then sliced, and these 3D models were parametrically made in Rhino. And we started with a very simple 20% overhang and wanted to work through how much it works, to the maximum overhang. So typical maximum overhang is around 20 degrees. So we printed here wet without any heating, without anything. 22 was achieved here, and with 27 even it's just falling down. We have a lot of possibilities to make it better. We can use firmwork. We can put some things there. So like usually in concrete and casting and whatever, we can use also fibers to improve the stability of the material. But we wanted to do it without it. We don't wanted to try to use hot air drying system. The other researchers also, what they did, in fact, is they used heat guns during the printing. So during the printing, they just heated the slices. So and the problem was here that the slices were dried too quickly, and it resulted into cracks. So this was quite a problem, and we wanted to see how we can solve this. So we have a robotic arm here. That's a universal robot that we had an extruder on as an end effector here. We use Machina as a software that is sending the path to the machine from Grasshopper. We use Grasshopper. It's a plugin for Rhino. That is what we use in architecture mostly. It's interesting really that this software is in fact even for robotics. We use quite a lot and try to avoid ROS or Move It or other software. But Grasshopper with Rhino is really perfect for this. And we developed 9 prototypes with different angles. Use clay with 20% chamot, and the extrusion speed was 20 millimeter per second. The aggregate inside chamot was 0.2 millimeters, very small, because the nozzle was 3 millimeters wide. We put heaters on the sides of the nozzle, and we could manually turn them on and off. Here are the heaters, and it's not a fan that's really directly fanning the slices. It's more about the surrounding air. Also, we had attached a thermal camera that was inspecting the heat. So here are the results. We have, without any problems, to be honest, really, it was really completely smooth, realized overhangs until 45 degrees, even 50 degrees. What we see here is a little buckle. And this is the result is not, in fact, the overhang by itself, but it's more the seam that we chosen here. We didn't chosen a spiral seam, a spiral extrusion. We choose a reverse extrusion thing that was an issue, in fact. So it was separated, and in the end, so it was too much pressure on it. So yeah, that was quite good. And what we could see really is that we could take off the material without any problem. After it was like having a 3D printed material out of plastic or something. So it was quite stiff and robust. Others than material that we print, it's still wet. We cannot touch it. We have to leave it there. Here, this thing you could just take it off and put it in the shelf for drying. So it was quite good. So what the thermal camera is in fact saying, we are not heating the slices, we are heating the surrounding air. So the surrounding air is heated up to 36 degrees, and the lab temperature, it was in middle in the winter. It was quite cold. We had an open window here, about 15 degrees in the lab. So we heated up the air until 36. On the left thermal image camera, you see an unheated process. On the right, the heated one. And the issue is in fact here really to warm up the printing bed, that is reflecting then the heat, to warm up the surrounding air. I think I'm just come to finish. So also speed affects in fact layer bonding. So if you are printing too quickly or too slow, it can affect the gluing together of the layers. Also, other climates will definitely change the way how we print and how it will be in fact how the overhang can work, and also the scale. So if we build in a bigger scale, it will also be quite different. So this is some things that we are going to test for the next research time. And one other thing I have to say, I mean, time is over, but I start a little bit later, is that we also wanted to add automated heaters. So not only put it on and off, but to be synchronized with the real-time temperature sensors and humidity sensor around. So this can be, in fact, be calibrated on the go. So this is what will really improve the overhang in also probably in bigger scales. So I think this is repeating what I said in fact now. Thank you very much. If you have any questions, I'm ready to answer you this.